Busy bee buzzes between the cells of a large honeycomb made up of a plane of tessellated hexagons. So a really good idea here is to get a sketch down and try and start thinking about how this is happening. A flight of length n consists of picking any of the six neighboring cells. So the bee might start here, for example, and flying to the nth cell in that direction. After consecutive flights of length capital N, n minus 1, and so on, the bee finds that it has returned to its starting location. For which values of capital N is this possible? So let's look at the case where capital N is equal to 1. Then the bee would simply fly one space and then stop. Can it get back to its original starting point? And the answer very quickly is no. Look, it goes down. No, it's not. It's not in the same place. It goes here. It's not in the same place. Okay, that's a good little starting point. What about when n is 2? We have to go 2 in one of the directions. Might as well go down 2. And then there's another flight that's 1 less than that. So potentially could go up by 1. But again, there's absolutely no way that the bee can get back to its starting point. I feel like that's enough justification. N equals 3. So let's go down 3. Well, actually, I haven't quite got enough space, have I? So that would be down 3. It would be this one here. Right, now the bee could actually go back up to and then back to here. So this one's going to be possible. We've managed to find a situation where it is possible. And I would keep going. I think it's a really good idea just to get a feel for whether it's possible. Are there going to be certain like multiples maybe or numbers that work and which don't work, or are they all going to be possible from here on? Let's try and find out. Along the way, try and develop some strategies. So if n is equal to 4, then what I thought is, okay, I'm going to go down and then sort of back up for 3. So I can get to this position after 2 moves. And then because I'm 1 away and I've noticed with 2, I ended up 1 away at the end, then I can clearly now I could carry on, I could go through it and then back. So that is definitely going to be possible. If I was doing this in a real thing, I'd probably just explain what I'm doing, and I wouldn't draw like a diagram for every single one because the diagrams are going to take a while to draw. As long as you kind of, I suppose you could just ignore the whole lattice and just focus on this bit here. It doesn't, the rest of the directions don't matter, but you can see n equals 4 is going to work. Okay, n equals 5. Right, now we can go down and back up again. That's going to be for 5 and 4. And then if I don't want to go now up 3 and down 2 because I'll end up at the start and then I won't be able to use that n equals 1. But if I go along 3 this way and back 2, then I can remain 1 away from the lattice. And then my last one takes me back to here. And again, I can see that it works. And I'm developing a strategy now. Let's test it out again. So can I just always stay 1 away? N equals 6. We're going to go down and back up to get to here. So that is 6 and 5. I'll start, maybe I should have been writing this. So 5 and 4 is here. And then I did 3 and 2. And I did 1. Whilst over here I did 4 and 3. And then 2 and 1. So now I've done 6 and 5. So if I do 4 and 3, I can get to there. And for 2 and 1 now, I'll go through it and back again. When I have to use that 2, I want to actually go through and back, whereas when I was just when I used 3 and 2, I wanted to remain 1 away, so I didn't want to go through it. Actually, yeah, I could have gone through it and back, to be fair. But in any case, it all works. So my conjecture, and this is what you have to do in maths. Sometimes we just have to conjecture that it is always conjecture true for n greater or equal to 3. And then we just have to justify why that is going to be possible. Okay, so here's my justification. So now I'm going to be looking at the general case n, where n is greater or equal to 3. So we're starting here. We're going to be going down and back up. So using n and n minus 1, we can move 1 away from the start. Then using n minus 2, n minus 3, we can remain 1 away. And we could just now kind of cycle round. So I can go up and then back down. That will again, each pair is basically just moving 1. Each pair, n each pair like together, that's the word I wanted, moves the B1 space. And therefore we continue around. You don't actually have to continue around, you can go back on yourself, but we might as well continue around. We continue around the start until we get to either 1 remaining, where we move to the start, so success, or to 1 remaining, where we move through the start and then back again, and then back to get to the start. And that's my proof complete. I think that's enough. Proof complete. N equals 1 and 2 fail. All other values of n, so n greater or equal to 3, are possible. Yeah, I was pretty pleased when I devised that. The answers do it in a slightly different way, talking about equilateral triangles. But I like this approach. Look, there's other ways to do it as long as like so. I think the summary is think about some cases, try and build up an idea of what's going on. That's what I've done here. When I got to n equals 6, I'd convinced myself that this is always going to be possible. And it's just a case of writing down a solid argument. I'm hoping, mine is sufficient and clear. So thank you for watching and well done on your efforts on this challenge.